Okay, hi, I'm here to talk to you about quantization of charge. And the idea of this is that charge comes in very specific amounts, packages basically, or I said discrete integer increments of E. So imagine this, the proton has a charge of plus E, right? And E is equal to 1.6 times 10 to the negative 19th coulombs. So the charge of a proton is 1.6 times 10 to the negative 19th. The charge of an electron is negative 1.6 times 10 to the negative 19th. And a neutron's got a charge of 0, so we can more or less ignore them. This might be your atom, right? Your neutrons are in the center. They are actually held together. I mean, you might think that neutrons will protons would repel each other because they're like charges. There's actually what we would call a strong force. It's called the strong force because it's actually quite strong. It's strong enough to hold them together despite the fact that they repel each other. And we'll talk a little bit more about that in the future. And then you got your electrons out here and kind of your electron cloud or your shell, depending on which theory you're following. And you could add everything together and you'd say, hey, the total charge of the nucleus is +2, the charge in the shell is -2e, and the total charge would be 0, right? Well, it doesn't always work out that they add up to 0, but what we do know is that they always come in discrete integer increments of E. So imagine this. Imagine you had, for example, 2 protons and 1 electron. Your total charge is going to be +2 minus 1 plus 1e, which is equal to 1.6 times 10 to the negative 19 coulombs. Totally cool. Let's say we had something, though, that wanted to look at a charge of 1/2 e. 1/2 e would have a charge of 1/2 times this, which would be 0.8 times 10 to the negative 18th coulombs. However, according to this, it can only come in discrete integer increments of E. So if an object claims to have a charge of 0.8 times 10 to the negative 19th, we know that it's not physically possible. It can't have a charge that is not an integer amount. So you could have a charge of 2e. That is perfectly okay. That's 3.2 times 10 to the negative 19th coulombs. 2.5e, though, is not, because it's not a discrete integer amount. You can't have a half of a proton or half of an electron. It just doesn't work out that way. And that would be a charge of 4 times 10 to the negative 19th coulombs. That is not possible. Boom. Something like 10e is totally okay. 10e would be 10 times 1.6 times 10 to the negative 19th coulombs, or a total of 1.6 times 10 to the negative 18th coulombs. That's okay. Check mark there, check mark there. However, e over 10, 1/10 e, that would be a charge of 1.6 times 10 to the negative 20th coulombs. That is not allowable because you cannot have a fractional amount of the elementary charge. You cannot have a fraction or a decimal of E, so not valid. In this case, if you want to figure out what the total charge is of an object, it's kind of a simple equation. It's not given on the reference table, but this might help you solve some of these questions. So imagine this, the total charge, I'm going to call that Q, is equal to N, which is the number of objects, N times the charge per object. I'm going to call the charge per object just lowercase q. So imagine if you had your thing and you said, hey, I want to know how many protons are in a charge of, let's say, 3.2 times 10 to the 20th coulombs. N, and we know that the charge of an electron, proton, I'm sorry, is 1.6 times 10 to the negative 19th. And so you solve for N. N equals 3.2 times 10 to the 20th divided by 1.6 times 10 to the negative 19th. Oh, I'm sorry, I meant to make that a negative 20. Otherwise that won't. So 3.2 times 10 to the negative 20th divided by 1.6 times 10 to the negative 19th should give you 2 times 10 to the negative 1, which is 0.2. It's telling you that you would have 0.2 or 20% of a proton. So that is not a valid number. It does not work. Not possible. So you can only have the discrete integer amounts. In case you're wondering how big a coulomb is, I'm going to erase this in just a second. A coulomb, let's say 1 coulomb, coulomb is equal to the number of protons times the charge of a proton. You could have negative 1 coulomb and change that to a negative 2. So negative coulomb is going to have the same number of electrons as a positive coulomb would have protons. So N equals 1 coulomb over 1.6 times 10 to the negative 19th. I'm going to put a C in there because I forgot that before. So you're 1 over 1.6 times 10 to the negative 19th. And that gets you 6.25 times 10 to the 18th protons. So that is a lot of protons, billions of protons, well, billions of protons in just that 1 coulomb. There's a lot of charge in there. Okay, I want to talk. Okay, I think that does it for this particular video. Thank you very much for watching.